So, again let me rewrite again. So, what we want is that this function psi, which is a wavelet, is n minus 1 times differentiable in the complex plane. So, the physical function is n minus 1 times continuously differentiable in the complex plane. So, which means in the transformed plane, which means that in the transformed plane my associated generating function m hat of omega has a 0, it has a 0 at omega equals pi, which is of order n. Okay. Well, where is this coming from? Note that m hat of pi is 0. Okay. So, at least we have a root of my associated generating function at pi, which is of order 1. So, if we want the original function to be n minus 1 times continuously differentiable, then its corresponding value in the transformed value of the associated generating function must vanish, must have at least one root which is of order n, one greater than the requirement. Okay. So, I have that this is already present. Okay. So, since there is one root at pi already present, if I were to have impose another requirement that this root is of order n, then I can get my original function to be n minus 1 times continuously differentiable. So, what I have is, so which means that I can describe my associated generating function. So, I can describe my associated generating function as follows. So, this is e to the power I omega by 2 to the power n times L hat omega. Okay. So, I see that this has a root at omega equals pi of order n. Okay. So, by introducing this factor, I have made sure that this associated generating function has a root of order n at omega equals pi. Okay. So, then now, so let me call this 4. So, this is a very important expression. So, I need to make sure that my new function L hat omega. So, which means that if I know what is this function L hat omega, I can plug it into this relation to get the associated generating function, and from the associated generating function I can create the scaling function phi and hence the wavelet psi. So, all I need is this function L hat of omega in the transformed plane. So, notice that L hat of omega is 2 pi periodic. Why? Because we are working in the discrete. So, this is for the discrete case of the Daubechies wavelet. I am working for 2 pi periodic in a 2 pi periodic domain. So, I need that my function L hat omega is 2 pi periodic. Also that in ideally my L hat omega must be n minus 1 times differentiable over the complex plane. Okay. So, if that is the case, I have made sure that my original function, which will be the inverse transform of this associated generating polynomial function times some other function, the original function in the physical plane will be also n minus 1 times continuously differentiable. So, I need these two conditions. Okay. So, I need these two conditions. Okay. So, let us look at what is the absolute value of this associated generating function. So, let us look at what is the absolute value of this associated generating function. So, let us work in terms of the square of the absolute value. So, I can, since this is a complex function in general, I can write this as m hat omega times m hat of minus omega. Okay. Notice that this is also equal to 1 plus e to the power negative I omega by 2 by the definition of m hat omega times, well, there is a factor of n. So, to the power n times 1 plus e to the power I omega by 2 to the power n times L hat omega times L hat minus omega. Okay. So, I have used the fact that the absolute value square is the product of the function with its conjugate. I see that this is also equal to this, the each of these factors when we multiply, I get that this is also equal to cos square omega by 2. So, I have simplified this expression. So, cos square omega by 2 to the power n times L hat omega to the power, well, L hat omega square. Okay. So, then I see, to begin with, I know that m hat omega is a polynomial. It is a polynomial in trig functions. Okay. It is a polynomial in trig, well, it is a function of all the trigonometric functions. So, it is a polynomial of the trig function, either sine or cosine, which means here I have got a cosine, and which means that L hat omega must also be a polynomial of trig functions. Okay. So, what we can assume? We can assume, without loss of generality, I can assume that my L hat of omega is a polynomial. It is a polynomial in cos omega. My L hat of omega is a polynomial in cos omega. We could assume that it is a polynomial in sin omega, but then sin and cos are related by a phase shift. So, that does not really matter. So, let us assume that L hat of omega is a polynomial in cos omega. So, then let us look at, so then what I have assumed is the following. I have assumed that L hat of omega is the square of the absolute value is some polynomial of cos of omega. Okay. So, where q is a polynomial. Okay. So, then now notice that I can rewrite my cos omega to be 1 minus sin square omega by 2, right. So, which means that my m hat omega, the absolute value of m hat omega square is nothing but cos square omega by 2 to the power n times L hat omega, well, L hat omega absolute value square, and this is also equal to cos square omega by 2 times, let me introduce q of 1 minus, well, q of 1 minus, it will be, well, this factor, there will be a factor of 2 here. So, q of 1 minus 2x, okay, where my x is sin square omega by 2. Okay. So, what I have shown here is, so notice that even, well, this is to the power n. Notice that even my cos square omega 2 is omega by 2, cos square omega by 2 is also 1 minus sin square omega by 2. So, which means that this m hat omega square can be written completely in terms of x. So, this is 1 minus x to the power n times q of 1 minus 2x. Okay. Okay. So, then also note the following. L hat of omega plus pi, L hat, if we take the absolute value and square it, L hat of omega plus pi, that is q of cos omega plus pi, that is q of cos omega plus pi, that is also q of negative cos omega. Well, all I have done is cos omega plus pi, replaced it with its function. And so, notice that instead of, so earlier when we had q of cos omega, I denoted by that equal to q of 1 minus 2x. So, all I have to do is take a minus. So, q of negative cos omega will become q of 2x minus 1. Okay. So, q of negative cos omega is q of 2x minus 1, and I see that this is also can be written as q of 1 minus 2 times 1 minus x. Okay. So, if I were to notice that this is also equal to 2x minus 1, or notice that this is also equal to a polynomial p of x minus 1. Okay. So, my polynomial where this I denote this quantity as p of x. Okay. So, I am denoting my q of 1 minus 2x as my polynomial p of x. So, I see that L hat of omega plus pi, the absolute value square, is polynomial at the argument 1 minus x. Okay. So, polynomial, same polynomial p. Okay. So, then recall the following property of my associated generating function. Recall that m hat of omega square plus m hat of omega plus pi. Again, so this is again via the reference. The associated generating function is going to satisfy this following equation. Again, if I were to plug what is m hat omega and I plug what is m hat omega plus pi, I get that this is also equal to, using the functional form of m hat omega, this is also equal to 1 minus x to the power n p n, well, x to the power n p of x, and m hat omega plus pi is going to be x to the power n times p of 1 minus x. Okay. So, this is equal to 1. Okay. So, let me call this my expression A. Notice that this is completely a polynomial equation, where p of x is a polynomial and multiplied by polynomial factors. Okay. So, I see that 1 minus x to the power n and x, these are all polynomials, okay, of degree n. Okay. Now, let me now also further, these are polynomials and they are relatively prime. Okay. So, now there is, if we were to find, it turns out that there is a unique solution, to this equation given by A. Okay. So, if I were to write this equation A, my A is 1 minus x to the power n p of x plus 1 plus x to the power n times p of 1 minus x is equal to 1. It turns out that there is a unique polynomial, solution of degree n minus 1. There is a unique polynomial solution of degree n minus 1. So, the polynomial solution is denoted by p n of x, okay, for equation given by A here. So, there is a unique polynomial solution of degree n minus 1 for equation A. I see that, well, readers, all my students and readers are directed to this following paper by Daubechies to see how this unique solution arises. Okay. So, please look at the paper published by Daubechies in 92 to see that a unique solution to 1 exists, and this unique solution is given by the following expression, which is summation k from 0 to n minus 1 times n plus k minus 1 c k x to the power k. Okay. So, this particular result is published in this particular paper the famous paper by Daubechies herself. Okay, so then I see that the degree of this polynomial is n minus 1. Okay. So which means let me call this expression B. Now so from B what I see is that p of x is a root for this particular polynomial given by A. So from B what I have is, since Pn of x is a root of C, well root of A, I have that Pn of x is nothing but the absolute value square of my polynomial L hat omega. Okay. So because it is the root, I get that Pn of x is L hat omega. Okay. So if I were to so all I am left with now is how to find out L hat omega from this function Pn of x. Okay. So I know that my Pn of x is also q, my polynomial of cos omega, or this is also polynomial in 1 minus 2x. So all I am left is how to construct this L hat omega, because from there I am going to construct my generating function and hence the scaling function or the Daubechies wavelet. Okay, so this question, the grand question that remains in this discussion is how to find L hat omega. Okay, so how to find the transformed value of this polynomial. Now we do not have to do much because there is a very nice result in the form of a lemma. So let me just highlight that result in the form of this Riesz spectral factorization lemma, which tells that if I am given a function, let me denote that function A hat omega. Let me call that this function can be represented as a polynomial of cosines. So A hat omega is a polynomial in terms of cosine. So this is a polynomial, it is a polynomial in cos of omega. Okay. So if I am given A hat of omega is a polynomial where all my coefficients ak's are real numbers, and further I have that an's are not 0, then and further I am given that A hat of omega is non-negative for all values of the argument which are real values. So I need that this polynomial is non-negative for all of its argument values, and well, let me write this, and A hat of 0 is 1. I am also further given that A hat of 0 is 1. So I have all these conditions. So I have a polynomial in omega given that all its coefficients are real, and the first coefficient is, well, the coefficients are non-zero, and also that the polynomial is non-negative, and that the value at omega equal to 0 the polynomial takes the value 1. Then what I get is the Riesz representation lemma tells that there exists a trigonometric polynomial L hat omega of the form summation bk e to the power I k omega, k from 0 to n. Okay. So I see that with real coefficients bk of bk's such that I have that L hat of 0 is 1, and most important is that L hat of omega is the factorization of A of omega. Okay. So L hat of omega is a factorization of A hat omega. So, most important is that this Riesz representation lemma tells me an important result. It tells me that if you give me a polynomial in cosine with all those conditions that I have specified, the lemma says that I can always factorize that polynomial to find my L hat omega, which will be used to generate the associated generating function. Okay, so let us look at an example now. So, let us look at an example on how to construct the Daubechies wavelet. Okay, so let me show you one example. Let me consider the case when n is 2. Okay. So, I am going to consider the case where I have vanishing moments up to order 2. So, which means my polynomial P2, which is a unique solution to my equation A, polynomial P2 of x is given to be the summation k from 0 to 1. It will be a polynomial of degree 1 or degree n minus 1. So, summation 0 to 1 k plus 1 c k x to the power k. This will be equal to 1 plus 2 x after putting in all the values, and then what I have is that L hat of omega, the absolute value square, will be P2 of omega. Okay. So, which means my polynomial P2 can be equated to L hat omega. Notice that P2 of omega is P2 of sine square omega by 2, or this is going to be, if I plug, so where if I plug my sine square omega by 2, so x is sine square omega by 2. So, P2 of omega is 1 plus 2 times sine square omega by 2. Okay. So, what I have is that I can rewrite my P2 of omega as 2 minus, let me rewrite this expression, this is going to be 2 minus cos omega. Okay. So, I see that this is also, let me write this L hat omega as L hat omega times L hat minus omega is 2 minus half e to the power I omega plus e to the power negative I omega. Okay. So, that, well, I can always write this sort of a representation comes as a direct implication by my Riesz factorization lemma that I have shown above. So, Riesz factorization lemma makes sure that I can always find L hat of omega directly from P2 of omega. So, let us now, so I know that, notice that my P2 of omega is a polynomial of order 1 with respect to this factor e to the power I omega, which means that my L hat of omega is also a polynomial. It is a polynomial of degree n minus 1. In this case, this will be equal to 1 of, well, with respect to e to the power negative I omega. Okay. So, with respect to this factor, my L hat of omega is a polynomial of degree 1. So, let me also assume that L hat of omega has this following representation. This is B0 plus B1 e to the power negative I omega. Okay. So, that is a polynomial of linear order. So, let us now use this expression in this equation to see what happens. I see that the following things happen. So, L hat of omega is B0 plus B1 e to the power negative I omega times B0 plus B1 e to the power plus I omega. This is also equated to P2. P2 is 2 minus half e to the power I omega plus e to the power negative I omega. Okay. So, then what I have is, if all I have to do is to find the coefficients B0 and B1. So, equating my coefficients, I get the following, that B0 square plus B1 square comes out to be 1 and B2 B0 B1 comes out to be negative 1. I see that if I were to solve these two equations, I get that B0 is 1/2 times 1 plus square root 3 and B1 is 1/2 times 1 minus square root 3. So, with this I have found my L hat omega. So, which means my generating function m hat of omega, is as follows. So, this is a polynomial of order 2 in e to the power I omega divided by 2 whole square times L hat of omega, which is B0 plus B1 e to the power negative I omega. Okay. So, then if I were to substitute B0 B1 and simplify all the expression, I get the following result. I get that my generating function m hat of omega comes out to be the following. This is 1 plus square root 3. So, this is after all the substitutions of B0 B1 and simplification. I get that this is this plus this times e to the power negative I omega plus 3 minus square root 3 times e to the power negative 2 I omega plus 1 minus square root 3 times e to the power negative 3 I omega. Okay. So, what I have is, I have this following polynomial of order 3. Okay. So, then students can also note and check that this generating function satisfies all the properties that we had to begin with, namely m hat of 0 is 1 and m hat of pi is 0. So, students are asked to check that indeed these two are satisfied. Okay. So, which means finally, I have to find out what is the wavelet. So, finally, my wavelet which is the Daubechies wavelet can be constructed as psi is given by this following summation n from negative infinity to infinity of dn times the scaling functions phi of 2x minus n, where my coefficients dn are nothing but negative 1 to the power n minus 1 times the complex conjugate of c, the coefficient cn's. Okay. So, cn's of 2n minus 1 minus n. So, notice that this is my C0, this is my C1, this is my C2 and this is my C3. So, all I have to do is to find the coefficients dn's from the cn's and plug it into this particular expression for to get my wavelet. Okay. So, in particular, if I were to solve, so my C0 is 1 by 4 square root 2 1 plus square root 3. Okay. So, well, notice that I have taken a factor of square root 2 out. So, hence it is not 1 by 8, but 1 by 4 square root 2, and then I can write C1 and C2 and C3. Okay. So, notice that my discussion on the wavelet with two orders of vanishing moments is complete. This in particular is called the Daubechies wavelet. This is the Daubechies wavelet D2. Okay. So, let us look at the particular scaling function. Let me show you the scaling function of D2. The scaling function of D2 versus x. So, it looks as follows. So, D2 has the following graph. It is some sort of an increasing function, say it is an increasing function up till 1 and then it decreases up till 2 and then it again starts to increase from 2 onwards. Okay. So, I see that this is the scaling function. I see that the resulting wavelet has vanishing moments up to order 2. Okay. So, that is my D2, and then we can similarly construct D4, D6 or any Dn and so on. Okay, so all we need is what is our requirement, and based on the requirement we say that the moments vanish, and from there we construct these scaling functions. Okay, so that completes my discussion on wavelet transforms, which is possible to the scope of this course. The students are also requested to see many interesting applications of wavelets which arises here. I have just highlighted some properties of these wavelets in particular cases. So, in this course we have looked at several different transforms. I hope this course is going to be helpful to a lot of students in engineering and sciences, and with this I conclude my discussion. Thank you very much. Thank you for listening.